Good morning, everyone. We'll start within the next minute. So, hi everyone. I hope you are well. About yesterday's exam, I should be able to begin correcting this week normally. You probably noticed. Well, you surely did. In the short answer questions, there were a few that involved calculations. I indicated at the top of the exam that some of the answers were made so they corresponded to a specific mistake in the solution. So these will receive partial credit. So I designed the answers so that I would know in advance what the error was. So don't worry about it. You will receive partial credit if that is indeed the answer you chose. It is not a black or white, all or nothing in these questions. Uh, so Today, we embark on the last leg of our journey, the last part of the third physics course in your Cégep, Modern Physics, the last part of its title. The main goal of this part is to challenge what you have been told, what you have learned so far, just to see that things aren't as clear as they sometimes seem to be, and sometimes our intuition may not be the right thing to follow. Since we live on a very specific scale, mainly ours is about a meter, 2 meters, we tend to experience phenomenon on this scale only. We don't have a large experience in what happens on very small scales. So this is mainly what we'll study in this part, and we'll see that sometimes things can be a bit unexpected from what we would intuitively expect them to be. So we'll divide this into two parts. In the first, we'll take a look at quantum mechanics. Mainly, our goal here will be to introduce why was this necessary? Why couldn't we continue studying physics like we always did? Like you did in the first two courses you took. Why couldn't we explain everything using the formalism of mechanics, of electromagnetism, as you studied it with Luc last semester? Why were changes necessary? So we'll introduce a few experimental evidence that showed scientists that indeed such a change was inevitable. And then we'll take a look at nuclear physics. So again, something that happens on a small scale. And again, we will challenge some of the things you have learned so far, not as much, but still a bit. And we'll be able to take a look at a few cool applications of this. So first, the first part we'll study this week and at the start of next week will be quantum mechanics. Uh, so the first part we'll take a look at. First, we'll put this into its historical context, see what was basically the notions that ran around at the time. Then we'll introduce here two experimental evidence that showed people that classical physics, classical physics was what was studied before, was not enough. So one, which I'll call the photoelectric effect, and the second, two very troubling words, electron waves. So before the start of the class, I put up a small question on the very first screen, asking you how you would represent an electron. So far, we study it as mainly a small ball or a single point at a singular location. We'll see that things aren't so clear after all. But first, the context. So quantum mechanics started to emerge at the end of the 19th century and the start of the 20th. So at the time, sorry, I forgot to put this into full screen. So right around this time was when electromagnetism was being heavily studied. So all of the phenomenon you studied with Luc last semester, magnetism, the potential, the electric field, the magnetic field, these were very heavily studied in the 19th century. So by the end, they were pretty well understood, and we had a very strong formalism of how to express them, how to predict what would happen in about every single case, except for very few exceptions. And also, well, mechanics ruled over the motion of every object since the 17th century. So this was again very well established, worked very well. We could explain the motion of the planets, of the stars, again using this. So this was very solid. Also, around this time was also the study of thermodynamics. So mainly the study of energy, of heat, of how it transfers from one object to another. And again, this was pretty well understood and led to huge leaps in the development of new technologies. So, like steam machines, steam works, and so on. All of these relied on on our understanding of energy and heat. So again, these new huge successes. This led to a general feeling that at the time physics was very well understood, as here Albert Michelson, in a quote often falsely attributed to Lord Kelvin, the same Kelvin that from which we took the degrees. So stated that the most important fundamental laws and facts of physical science have all been discovered, and these are so firmly established that the possibility of their even being supplanted in consequence of new discoveries is exceedingly remote. So there could be maybe some adjustments because there were a few corner cases in which we had problems. So this was admitted, but in general, the fundamentals was believed should not be touched anymore. They were pretty well understood. But as stated, there were a few corner cases in which the theory, as we understood it, failed. But it was thought that mainly with small adjustments, we could explain those. For instance, whenever we took electromagnetism, which was again very well understood, we had a strong mathematical background to express it. Whenever we studied what happened in another frame of reference, remember when we studied waves at the start of the semester, we talked briefly about a frame of reference, which was mainly a point of view. So depending on your velocity, you had a different point of view on a given phenomenon. But still, no matter your point of view, this should not affect the result of an experiment. You should still have the same result no matter the velocity you're going at. You may adapt how things translate from your point of view to that of another, but there should not be any discrepancies between these. But then, whenever we took electromagnetism, tried to do calculation in a frame of reference, and using what we used at the start of the semester just to transfer to another frame of reference, result didn't match. So it was thought that we would need small adjustments to it again. Another things, Newtonian's mechanics could, as stated, very well explain the motion of planets, of stars, and so on. There were sometimes very small differences between the observations and the calculations. For instance, when studying the orbit of Mercury, there was a small difference of about where it should have been compared to what it actually was, of 42 seconds of arc per century. So a second of arc. Imagine a circle with 360 degrees, take one of these degrees, divide it into 60 equal parts. You have a minute of arc. Take the 60th of a degree, divide it once again into 60 equal parts. You get a second of arc. So basically, we had 42 times, a degree is, sorry, my bad. So a second is 1/60th of 1/60th of a degree. So 1/3060th of a degree per century. Not bad, actually not bad. It could have been from an uncertainty in the observation, but is what it was observed each and every single time. So it was not just in one experiment, but in all of them. So again, not a huge difference. Maybe some small adjustment could do it. Also, whenever we studied the electrical resistance at room temperature, we could study it as you studied in electromagnetism. So it is what the resistance, the electrical resistance is what impedes electrical current from going through a given material. So, at our scale, at our usual temperature, we can study it using Ohm's law, for instance. And then whenever we decreased the temperature to very, very low temperature, close to 0 Kelvin, for some material, the resistance dropped to 0. And even when we tried to have more and more precise measurements, we still found 0. Not a very small resistance, a flat 0. But again, we don't usually live at 0 degree Kelvin, so not that important, at least at first glance. And last but not least, we studied in the second part of the course light, first as a ray, and second as an electromagnetic wave. There were a few experiments in which treating light as a wave, as we knew it, like an oscillating pattern that travels and all of the pattern hits a given object, was not exactly sufficient to explain what was observed experimentally. But again, it was not in all cases, just in a few of them. Still, all of these corner cases gave rise to their own field of physics, their own new fields, which had not started until that period of time, until the start of the 20th century. So this started turn by turn. Special relativity, so mainly what happens when you go very, very fast, close to the speed of light. The observation of object in space, of planets, of star, of Mercury in this case, gave rise to general relativity. So special relativity deals with constant velocities. General relativity deals with non-constant velocities. So in cases with acceleration, so it is generally used as a better theory of gravity than what Newton first developed. The third point gave rise to superconductivity, which is the study of exactly this. Why do some material have a zero resistance at low temperature, and how can we find some materials that would have this property at higher temperature? And the last one will be the one we'll study here, quantum mechanics. So the study of how what we first is this too much of a spoiler? Yes, I'll say it. So the study of how what we first, from our point of view, treated as particles, object with a very well-defined positions, and waves, what we studied in the first part of the course. So sound, waves on ropes, light as we first studied it, and we studied it as two very different objects. They're not that detached from each other as what was first believed. So we'll blur things a bit. You might come out of this feeling that you understand less than what you started with. This is normal. This is a bit the point of the things, the exercise. things aren't as clear as we first thought they were. But first, we'll take a look at, well, why do we need to do this in the first place? This I'll already talked about. Before we move on to what I'll call the photoelectric effect, would you have something you'd like to ask, a comment you'd like to make? As always, if it comes to you later on, please do not hesitate to write it down in the chat. I'm always keeping an eye on it from the corner of my eye. If your question feels like it would be long to write down, you can quickly write question, and then I'll know that I have to wait for you to finish typing. So the first experimental evidence we had was this one. So by around the end of the 90th century, there were some experiments still related to electromagnetism, for instance, in which we had two electrodes with a difference in potential between the two. And it was observed that whenever, well, first, as you've seen in electromagnetism, if you put a large enough difference of potential between these two, at some point you'll be able to rip some electrons from one location and bring them to the other. So from the point with the lowest potential to the one to the largest, we'll be able to rip some of them. Here, this is basically a capacitor, and past some potential difference, you get some current that can go through it. It was observed that whenever we shone light on the one from the electrode from which electrons were ripped off, this was easier to do. We needed a smaller potential to achieve the same result. So the study went on. We could measure how many electrons were ripped from the electron with the current through it. Basically, the current is the measure of how many charges go through a given section of the wire per unit of time. And since each electron carries its own charge, knowing the current, we could deduce how many electrons went by. We could know whenever we had more or less in this case. Also, what was observed is if we still shone light on one of the electrons, but inverted the polarity of the two electrodes. So mainly, instead of having the left one being at a lower potential than the right one, it was inversed. This one had a lower potential than this one. And if we still shone light on the leftmost one, so it was observed that whenever light was shown, we could still rip off some electrons from this, and by tuning the potential between the two. Since, from the point of view of an electron, it is better to be at a higher potential than at a lower one, if the potential difference is not too big by shining light on it, the electrons could still start from here, reach here, continue, and come back. Otherwise, I'm having a blank here. Yeah. Otherwise, if the difference was too great, they could not go from one side to the other. And if you tuned the potential difference between the two electrodes, just so if you started low enough, you got some current and increase the difference up to the one point until you got no current. This was a mean of finding the kinetic electron, the kinetic energy of the electron that were ejected from this material through the conservation of energy. So the difference between the potential energy of these two locations. So the potential energy is the charge of the particle times the potential at the location it is. So the difference between the potential energy here and here is the charge here of the particle, so the charge of the electron in absolute value, and times the difference between the two potentials, so the difference, basically the voltage. And whenever we have zero current, and this is the first time we have it, we get a measure of what was the maximum kinetic energy of the electrons that were ripped off the material. So some of them have a lower kinetic energy, some of them have a larger one. And whenever we get zero current, that means that even the most energetic one could not reach the rightmost electrode. So from this, we could get an experimental value of the maximum kinetic energy of the electrons that were ejected from the electrode, using what we'll call the stopping voltage. So whenever we use delta V0, it is a stopping voltage, a voltage at which we start having zero current, so none of the electrons manage to get to the second electrode. All right, so we could light could, it seems so, rip electrons off a surface. Even this we could explain using what we knew at this point. So here, I'll explain the diagram. What I represented here, I have two axes, one of energy, and one here of the position I called R. So at the time, we were suspecting that matter was made of atoms. So what I represented here at position R equals 0 is the center of the atom, what we would nowadays call the nucleus. At the time, it wasn't clear that there was a nucleus and an atom, so far it was just the center of it. And we knew that inside of it were electrons. We're not sure how they were dispatched. Were they evenly spread? Were there the concept of atomic levels of orbitals was not known at all. So we just knew that there were some electrons, and that's it. We knew that they were around there. So what I plotted here in blue is the potential energy of electrons, so that it is very low. Here, in fact, the graph even cuts off as it gets lower and lower, so that it is better for the electrons to stay around the atom. So this is a representation of electrons being in the atom, basically. And we knew, well, from the experimental results, that not all the electrons had the same energy inside of the atom. Some had a lower one, some had a higher one. Nowadays, we would say that, well, all of them are on atomic energy levels, and some of them are on lower levels, some of them are on higher levels. But all we could say at the time is there is some maximum energy inside of the atom in which some electrons are. There are others at lower energy. We don't know their energy precisely, but we know there are some below and none above the maximum energy that they are within. And this energy is the sum of potential and kinetic. So basically, the electrons, since they are near the atom, have some potential energy and are moving a bit around. So they have, in addition to the potential energy, some kinetic energy, which gives this total maximum energy. And what being bound to an atom means, it means having an energy that is lower than 0. So as long as the electron is in this part of the graph, it is bound to the atom. But if it were to gain some energy and be able to have a positive energy, it would be freed from the electron, from the attraction of the nucleus from the atom. And the energy that separates it from freedom we'll call phi the work function. So this is the energy that is needed to free the electrons in the material that already have the largest energy out of them all. We can compare this to what would happen to if we had a ball at the bottom of a well. If you want to take out the ball, you have to give it energy of at least what it needs in terms of potential energy to take it from the bottom and bring out to the top. This is the same thing. You take an electron at this energy, you have to bring it out to a zero energy over here. So same here, it is at here minus mgh. If the ball has a mass m, you have to bring it up to zero in order to take it out of the well. And if you give it more energy than it needs, if instead of just giving the electron here, again, I'll always focus on the most energetic ones. So keep in mind there are other below, but I'll focus the discussion on this one. If you give it more energy than it needs to be freed, the remainder will be converted to kinetic energy. So let's say I give it this amount of energy, it just needs this to be freed, and the rest takes the form of kinetic energy. In this case, since it was the most energetic one, out of all the electrons that are below, it will be the one that will have the most energy in the end. If it starts lower, it will, after absorbing the same amount of energy, have a lower kinetic energy. And at some point, even if you go low enough, it won't even be freed anymore. So the name we give to this phenomenon of by shining light on a material, of ripping off electrons of it, is the photoelectric effect. So this is what was observed. Was observed in our experiment with the electrode. So the electrode is made of a certain material, and this material is made of atoms, which contains electrons. So we knew at the time that a wave, any kind of wave, light, sound, a wave on the surface of the water, anything, carries some amount of energy. So we already knew that this wave, light in this case, could give energy to the electrons, rip them off the material, free them, and make them go to the second electrode. No problem, at least in the most basic level of the explanation. But when we got into the details, things started to get ugly. First, from the classical point of view, from what we understood with a classical wave at the time, well, first, with what contributes to the energy. In a classical wave, what contributes to the energy of the wave? Well, a way to represent, to imagine the energy that a wave contains is to study how it can transfer the energy. So it cannot transfer energy that it didn't have in the first place. So we'll focus our analysis on the energy that is transferred to an object. And to do this, we'll imagine a wave on the surface of the water and a small boat on the surface. So let's say you have huge waves coming up and down on the ocean and a small boat on the surface. So energy can take different forms. It can be kinetic energy, it can be potential energy, it can be used to deform objects, can be used to transfer heat. So a whole bunch of forms. In most cases, it is a bit difficult to analyze because we have a lot of forms of energy all at once. So again, to simplify, we'll take a look at one specific time in this phenomenon of the wave oscillating up and down with the boat, the time at which the boat reaches its highest point. So the wave is oscillating, and the boat, let's say we'll forget that it is moving left and right. Just focus on its up and down motion, and focus at the point at which it is the highest. So when it is the highest, it is the position at which it has the greatest potential energy. It has no kinetic energy, no other form of energy, so all of it is potential energy. So we'll focus on this one to simplify the analysis. And what defines how high it reaches is the amplitude of the wave on the surface of the water. The greater the amplitude, the higher the boat will reach. The smaller the amplitude, the lower the boat will reach. So in a classical wave, what defines the energy that it can transfer is its amplitude. And so the energy it has is also defined by its amplitude. The greater the amplitude of a wave, the more energy it contains. Same thing with the sound. So whenever you shout instead of just speaking softly, you shout a wave with a larger amplitude, with a larger volume, so it has more energy. But at least if you don't change the pitch, it should have the same frequency, the same wavelength, travel the same speed. All the rest stays the same, but it carries a larger amount of energy. And all of the other parameters, the frequency, wavelength, and so on, do not influence the energy in a classical wave. And last thing, what we call the intensity of the, like what we studied in the second part of the course, the intensity of the light was linked to the amplitude of the wave. Mathematically, it is the amplitude squared, but you can just think of it, the larger amplitude, the larger the intensity. Whenever we got a pattern on the screen, we had a non-zero intensity when the amplitude was non-zero. So when we had constructed interference, we had zero intensity whenever the amplitude was zero, whenever we had destructive interference. So this was linked to the amplitude of the wave, to the intensity. So through this, from what we understood, if we played around with the intensity of the light, if we turned up the intensity, we should transfer more energy to the electrons. We should have a larger maximum kinetic energy. Since the reminder, if you increase the energy that is absorbed, if the electron ends up over here, or instead, the kinetic energy will be larger. And in the other way around, if we lower the intensity, we should have a lower maximum kinetic energy for the specific light. Also, since, let's say, if we send light on it, if we keep sending a wave on it, from the classical point of view, it will take some time for the electron to absorb energy, until the time it has enough to free itself. And this time should increase the lower the intensity is, since if the intensity is low, well, at any given time, the electron receives less energy, so it should have to wait longer for it to be freed. So we expected some kind of delay due to this. And again, the frequency should not have any influence on this, since the energy should only depend on the amplitude, on the intensity. So even we change the frequency and thus the wavelength, if we switched from green light to red to ultraviolet to X-rays, it should not change anything, because all of these just differ by their wavelength and their frequency. But this formalism, which was pretty well established in the study of waves so far, completely failed to explain what was observed. What was observed was instead the following. Even when we played around with the intensity, increased it as much as we could, decreased it as much as we could, it didn't have any impact on the maximum kinetic energy, which again we couldn't measure. We couldn't measure with the stopping potential. So no influence, none at all. Didn't seem to have an influence on the energy of the electrons. Instead, what had the largest impact was the frequency. When we change the frequency, This changed the maximum kinetic energy. And most troubling of all, if we decrease the frequency more and more and more, let's say we started with X-rays, we went down to ultraviolet, went down to normal violet, blue, green, and so on. At some point, below a certain frequency, nothing was ripped off the electron. No electron ejected at all. And also the delay, which we expected due to the fact that electrons had to build up some energy before being able to be freed, was not measured. Maybe it was there, very, very small, but at least it was not measurable. So what we understood at the time failed to explain this phenomenon. To do this, first, before I give the answer, let's think at it all. So, if we have no delay, that means that the electrons that are ejected get all the energy they need in one single moment. So you do not have to keep absorbing. So instead of energy being spread out along all of the wave we send, that means we can imagine it as being condensed in a small packet that can be absorbed at one single time. Also, to solve the problem, since the maximum kinetic energy depended on the frequency and not on the intensity, so not on the amplitude of the wave, the object that will save our hides here should have its energy depend on the frequency, so that whenever the frequency of the light is greater, the energy of this object is greater, the electron gains a greater energy by absorbing it, and if the frequency gets lower, the energy gets lower also. The electron gains less energy. Let me introduce you to the photon. The photon is the object that solved this problem. It is defined as a tiny energy packet that can be absorbed all at once and that exhibits not a wave-like pattern as we have studied light so far, but behaves much like a particle. So you can imagine it very much as a small packet of energy that is not, you cannot divide it in multiple parts. It begins with, it is made up of one single bundle, stays that way until the absorbed. And the energy of this photon is given, so E here is the energy of the photon, is given by H, which will be our new best friend for everything related to quantum mechanics, the Planck constant, times F, the frequency of this photon. So the greater the frequency, the greater the energy. H, the Planck constant, is measured in units of energy times second. Here I gave you two different units of energy. The first one we're used to, joules times second, in which the Planck constant takes this value, so 6.626 times 10 to the minus 34. Also, some units will work a lot from now on in quantum mechanics and in nuclear physics, electron volts. So they're mainly designed to make small energy easier to work with. We could also write this, the Planck constant, in units of electron volts times second, using this factor of convergence. So 1 electron volt is equal to 1.602 times 10 to minus 19 joules. This factor you've probably seen before. Do you recognize it? No is a valid answer. So please don't hesitate if that is the case. Yes, exactly, Jonathan. It is the charge of an electron. It is the elementary charge. So basically, when we say 1 electron volt, we basically read it 1 times the elementary charge times 1 volt. So this is why the factor between the two, yeah, proton, yeah, same thing. So it is just the factor between the two. So 1 times the elementary charge times 1 volt gives us the value of energy in joules. And this solved our problem because at any given time, an electron will absorb 1 photon. If this photon was enough to free the electron, it is free from the atom, can go wherever it wants, and the remainder of energy, if it has any, would be in the form of kinetic energy. If an electron cannot, at least not in the general case, absorb more than 1 photon at a time. There are a very small probability that it can, but we'll neglect it. Uh, so from this, we could better explain why we have no delay. So as soon as a photon is absorbed, the electron is ejected, and we had the dependency on the frequency, none on the intensity. This fits pretty well. So whenever we shine a beam of light, it is in fact composed of a bunch of photons. But two, do I say this right away? I'll have to in a second. So I'll do that in the next slide. So whenever we send a beam of light, which contains some total amount of energy, the energy is divided between all of the photons it carries. So we will define the number of photons in a given beam of light, knowing the energy of a single photon, which is what we introduced in the last slide, the Planck constant times the frequency. So, we'll divide the total energy of the beam of light by the energy of a single photon. If all of those have the same energy, meaning if we have a single frequency, this will give us the number of photons in it. And the total energy in a beam of light will define, using intensity, the area that is being lit and the time during which we light the surface. The logic is the following. An intensity is measured in watts per meter squared. So first, we cancel out the meter squared by multiplying by the area. So with this, we end up with watts. Watts is a measure of a power, so an energy per unit of time. And to get rid of the per unit of time, we multiply it by the time during which we light the surface. So all of this becomes the energy that was transferred by the ray of light on a given surface during a certain amount of time. And so if you increase the intensity of the light while keeping the frequency constant, basically you're just sending more photons with the same energy. So the electrons won't gain more energy, but you'll just free more of them. And to go back to our formalism with an atom, electrons in it, the energy it takes to free the ones that have the most energy and the maximum kinetic energy. What we had first written as the energy absorbed, we can now write with an expression knowing that it is the energy of a photon, because a photon is what is absorbed. So HF is the energy that is absorbed by the electron. So HF equals phi plus K max. So we have another expression of the maximum kinetic energy. It is all of which was absorbed minus what was used to free the electron. And from this, we can also write down what is the minimum energy we need to free the electron. This is phi, the work function. And again, we can find the frequency of an electron, the frequency of a photon, that will be needed to just free this electron, well, the energy of the photon needs to be exactly equal to the wave function. So we need a frequency f0, which we'll call the threshold frequency, which is just enough to have this energy. And from this frequency, sometimes we'll be told to find the threshold wavelength. This is the wavelength associated with the threshold frequency. We can play around with what we first introduced in the first part of the class. And the speed of a wave is equal to the wavelength times the frequency. You can find the wavelength using this. So, did I skip something? I had something else to say. Okay. Well, so it looks like what I waited for, I forgot to add at the last minute. So basically, uh, in the second part of the course, we studied light as a wave, and I was very careful with my wording whenever I first introduced light. I said that light travels as an electromagnetic wave. Here, what we saw, we did not destroy the statement. We did not redefine how light travels. We redefine how light is absorbed. We redefine how light interacts how light behaves whenever it interacts with something here, with an electron. And whenever it does, we needed it to act as a small packet, as a very small contained package, as a particle. So the photoelectric effect, was one of the experimental evidence that light was not clearly a wave, as was the result of the whole debate that took place in the 80th and 90th century, was not clearly a stream of particle, which was the opposite side in this debate. But in fact, it depends. It depends on where or when you're looking at it. If you're looking at when it travels, it indeed behaves as a wave. But when it is interacting, it behaves as a particle. So this is what we call a wave-particle duality, which the photoelectric effect was one of the main evidence for light. So on this, would you have some questions, comments? Otherwise, what I do, we could take what I do. I'd probably take a 5 minutes break now. I'll arrange a setup. We'll do one example based on this. Then after this example, I'll take another 5 minutes break to rearrange my setup, and we'll take a look at the last two troubling words at the top of the screen, the electron waves. If that is all right with you, I'd see you in about 5 minutes. Would you be ready to start again? All right. So in addition to the example listed in the presentation, here we'll actually do an exercise. I suggest we take a look at exercise 38.9 on page 1275. 38.9. In which we are told the following. I'll give you a few seconds to take out your books if you want to read it for yourself. So when ultraviolet light with a wavelength of 400 nanometers, I'll write it down before I forget. So a nanometer, again, is 10 to the power minus 9 meters. Falls on a certain metal surface. The maximum kinetic energy of the emitted photoelectron. So a photoelectron is just an electron. They just gave it another name because it was ejected through the photoelectric effect, which is just an electron. Is measured to be 1.10 electron volts. 1.10 electron volts. What is the maximum kinetic energy of the electrons that are ejected when light of wavelength 300 nanometers falls on the same surface? So we have two different situations. So in the first two parameters I wrote down, I'll just come back and add small indices. 1, and for the second one, with a wavelength of 300 nanometers, so which is equal to 300 times 10 to the minus 9 meter. We want to know what will be the maximum kinetic energy for this wavelength. The logic is the following. We know that the maximum kinetic energy can be written as the energy of the photon that was absorbed minus what was needed to free the electron. So, knowing the wavelength, we'll be able to find the frequency. So the first case, using the parameters we're told, will be a way to find phi, the wave function. The wave function is the energy it takes to free an electron from a surface. It only depends on the material. Basically, it depends on how much energy does the most energetic electrons have. This depends, from our current knowledge, of how the atomic layers are filled and how many electrons there are. So this depends on the material. As long as you don't change the material, this stays the same. So this will stay the same for the second part of the problem. We're able to take it, recycle our value, and find Kmax in the second part of the problem. So this is where we are heading. Before we do that, we have to transform this a bit to talk in terms of wavelengths instead of frequencies. So we know that the speed of a wave is given by its wavelength times its frequency. If we're studying light, and if we suppose we are, at least in most part, in vacuum, the speed of the wave is equal to the speed of light in vacuum. Even within a given material, whenever we we say that light has different speed in different materials, it means that light is slowed down because it keeps getting absorbed and emitted all the time. It slows down its path. But most of the material is made of vacuum. So we'll take C. In this case, as long as the light is not absorbed by an electron, it will go at the speed of C. And from this, we'll be able to write down the frequency as C over lambda. Plug this back in here and write this as hc over lambda minus pi. All right. Are we done? Not quite. Because h, we have values for it. C, we have value for it. Lambda, we're given. This, we want to find. Kmax. Yes, we were given a value, but it was given to us in electron volts, which is not an SI unit. So, we have two possibilities. The first one, we transfer this into SI units, into joules, work into joules, find a phi in joules, looking back, and then transfer our final result back in electron volts. Or we can also use the value of H in electron volts. If we do this, the value of phi we'll find will also be in electron volts. Both methods will give the same final answer. Here I'll transfer Kmax into joules. So it was said to us that it was equal to 1.10 electron volts. 1 electron volt is 1.602 times 10 to the minus 19 joule. This gives us 1.1 times 1.602, 1.7622 times 10 to the minus 19 joule. This is why electron volts are useful. We don't have to keep this factor around, but we'll work with it here. So we have 1.722 times 10, I forgot a 6, sorry, I forgot a 6, times 10 to the minus 19 is equal to H, the Planck constant, 6.626 times 10 to the minus 34, times C, the speed of light in vacuum, which is 3, times 10 to the power 8, over the wavelength, which is 400 times 10 to the minus 9. All of this, here I don't have in a space, minus phi. So we find that phi is equal to, I bring this down here, bring this out on the left side. This gives 34, 8, 9. So 9 plus 8 is 17. Minus 34 plus 17 is minus 17. So I'll have 6.626 times 3 over 400 point. Let's say this minus this. 622 times 10 to the minus 19. So this is 4.97 times 10 to the power 19, which gives me 3.2073 times 10 to the power minus 19 joule. So this defined our material. We can now use this in our initial case. In the second case, sorry. So in the second case, we want to find Kmax 2, which is equal to the same Planck constant, the same speed of light, over the second wavelength, minus the phi we just found. So we just plug in what we know. Again, this is 6.626 times 10 to the minus 34 times 3 times 10 to the power 8 over, and now we just have 300 nanometers. And all of this minus what we found, minus what is needed to free an electron from this material. And again, using our trusty calculator. Okay, I can't really write on the back now. All right. I'll have to reuse this somehow. So from this, Kmax with the second wavelength will be equal to 3.4187 times 10 to the minus 19 joule. Again, we'll transfer it into electron volts. Most of the time, the textbook will give you the answers in electron volts. So make sure to transfer it. We know that 1 electron volt is equal to 1.602 times 10 to the power minus 19. The 2 power minus 19 cancel. I don't even have to bother with them. And this gives me 2.134 electron volts. So this is the maximum kinetic energy that our electrons will have with the second wavelength. Knowing that the first wavelength was greater than the second, that we got Kmax 1 was less than Kmax 2. Does this make sense to you from what we have studied, that an electron absorbs a photon of a given energy and is freed? What energy it has left after being freed is kinetic energy. Does this make sense? Basically, the logic is, if the first wavelength is greater than the second, wavelength and frequency vary as the inverse of each other. So if the first wavelength was greater, the first frequency is less than the second. You can say this using lambda is equal to C over F. So the greater F, the lesser lambda. And through our expression of the energy of a photon, this means that the first photon had a small energy than the second. And what happens in this case, we have E equals 0, the barrier between being bound and freed. Phi, I'll draw two cases. In the first case, the electron absorbed some energy. HF1 went here with a given Kmax. In the other case, the energy of the photon was greater. So the electron ended up with a greater maximum kinetic energy because the energy it absorbed was greater in the second case than in the first. And that would bring us to the end of this exercise. Questions or comments on this? Otherwise, I'd go for a second 5 minutes break so I can rearrange my setup and do the last part of the presentation. I'll see you in approximately All right, we'll start again shortly. So, um, the photography effect was one experimental evidence that light could not be studied purely as a wave in all of its aspects, purely as a particle in all of its aspects, but it depended on what part of its behavior we were looking at. There were other evidence which I didn't show here. If you're interested, you can look in your textbook on the black body radiation and the Compton scattering. These were other types of experimental evidence which further confirmed that we had to treat light, in part at least, as a bunch of particles. So this raised the question: if light, which after years and decades of debate was finally defined as a wave, and then once again broken down. If light could behave as both a wave and a particle, could the same happen to matter? So this question was raised by a young French physicist called Louis de Broglie. This is written Broglie. However, please, it is pronounced Broglie. It is due to his family was Italian. They worked how they wrote their last name, but kept the pronunciation inspired by the original pronunciation Broglia. So this is why it was pronounced Broglie. So in his PhD, here is the question: could it happen with matter? So went on with this delirium and ended up with a wavelength, now named after him, the Broglie wavelength, which is defined as the Planck constant over the momentum. And this is the wavelength, not of some kind of wave which was already studied, but this also applies to it, but not exclusively. But the wavelength of a particle, if we decided to study it as a wave. So we came up with this. This also applies to other types of waves. So sometimes in the exercises, you will be told, for instance, to find the momentum of a photon. Since a photon does not have a mass, it is not made of matter, it is just a bunch of energy. The classical expression we have for the momentum, which I'll remind in the next slide, is the mass times the velocity. Does not apply for a photon. But this expression is a way you can find the momentum of a photon knowing its wavelength. So this applies to every kind of particle, whether it is matter, a photon, anything else. Here I remind you, the expression of the momentum is equal to mass times velocity. Okay, I'll go directly to this. I'll do the demonstration afterwards. So if instead we could treat matter as a wave, well, we should still be able to find some experimental evidence that this made sense and was not just a way to get a PhD easy. So they did an experiment in which, well, I don't remember who exactly did it, so that's why I'm using they, in which they threw electrons through a thin sheet of aluminum and saw what they could get on a screen located further ahead. On the right is the result they got. So here we have a color scale. In the center, this means that around this location, they got a lot of electrons. There were some other parts in which they got a very low number of electrons. A lot, not a lot. A lot, not a lot. A lot, not a lot. So the key point here is the electrons were thrown through either one or a bunch of very small apertures, mainly apertures between atoms in the lattice of the metal. So the metal is made of a bunch of atoms. The electrons passed through these atoms. This is similar to something we've studied. At least we studied in a slightly different context. We'll go back to it just to show how it is linked. We studied last week diffraction, which was how light behaved whenever it crossed a slit of a given width. So we constructed a slit, observed a pattern with bright parts, dark parts, bright, part, dark, and so on. And we mainly focused our study on a thin slit. But we will get diffraction no matter the form of the aperture we're using. We could use one shaped like a person, get some pattern of diffraction on the screen. We could use a circle and a square. We could use a circular aperture. So a single aperture through which light can go through, and we get a pattern on the screen. In this pattern, we have a very bright spot in the middle, circular and dark, bright, which form rings. This is the same thing we get whenever we try to send electrons or neutrons, also any kind of particle, through a given sheet of a material. You also have a figure of actual experimental data. So this is here on the slide, this is a figure I created myself. But in your textbook, you have a figure of actual experimental data of diffraction using particles. And we get this pattern. Okay? So we can get the diffraction pattern using what we usually see as particles. So what? Well, in our study of interference and diffraction, in order to explain it for light, we had to treat light as a wave. And whenever we had bright spots, this meant we have constructive interference, dark spot, destructive interference. If we get a diffraction pattern using electrons, neutrons, and so on, this means that the particles we sent also underwent interference. And since they underwent interference, they behaved also as waves, just like light did in our experiment. So whenever the electrons traveled through the slit, through a thin layer of material, they traveled as a wave. Now again, we'll have, just like in the case of a light, a duality, a wave-particle duality. What we consider as matter also travels as a wave. So whenever it is not interacting, it is a wave. But when it interacts with something, just like when it hits the screen, now we get a hit on one particular spot on the screen, it behaves as a particle. Just like the photon, light travels as a wave, is absorbed, interacts as a particle. Matter, whenever it is not interacting, acts as a wave. When it interacts, acts as a particle. So whenever I presented the figure, so mainly we had a lot of hits. So we had 1, 2, 3, 4, a million electrons in the center. Very few here, a lot here, very few here. So it's not bright and dark spots as we had for light, but how many electrons we got. But it is still the same principle. I had something to say on this. I'll also illustrate it. 1 second. So we could also picture it with interference. We can also have interference if we have diffraction. So here I have two thin slits, a screen in the middle of the screen. So whenever we run the experiment, we get first, let's say, we detect an electron here. All right. We do the experiment a second time. We get the electron here. All right. Third time, oops. Here, another time, again here, another time here, and so on. So that whenever we combine the result of many experiments, we get something like this, with spots in which we got a lot of electrons, other at which we got very few. And we can, from this, find a pattern of areas in which we had a lot of electrons and other in which we didn't have a lot at all. So here I don't have exactly the right regularity since I did it on the fly, but we get pretty much the same thing. I had something else, I had something else, I had something else. So yeah, so before doing the experiment, we don't know exactly where we'll get an electron. As we had in the thing we had, might end up in some part, might end up in some other part. So the wave-like behavior of matter has a sense of the probability at which we will detect this particle whenever we try to measure it. So whenever we have a wave with a large amplitude, that means we'll have a bigger probability of finding the particle there. Whenever we have a lesser amplitude, whenever we have, for instance, destructive interference, that means we'll have a very low or zero probability of finding the particle there after doing a measurement. On the particle, on the electronic waves and the waves of matter, here I give you a few examples. The exercises are in general very short. Mainly, you just apply the equation of the de Broglie wavelength, the equation of momentum. Sometimes you may have to remember the equation of the kinetic energy, so 1/2 m times the velocity squared. This is all you need. What we just discussed on the wave-like behavior of what we generally conceived as particles will have an incidence on our understanding of how atoms work, mainly next week. So I had a slide, but I want to rework it before presenting it to you. This will be our key to explain why atoms have energy levels. Why do they have orbitals in the first place? We will need electrons to behave like waves to explain it. So this is what we'll start off with next week. We'll study it and then briefly study the hydrogen atom once we establish why there are energy levels in the first place. So before we wrap up for today, would you have any last comments, any last questions before we say goodbye? Tomorrow, I'll be available from 5 to 6 to answer your questions on Zoom if you have any. Otherwise, I think that will be all for today. So thank you for being here today, and Well, I'll see you tomorrow if you want to. Otherwise, I'll see you on Monday. Camera's there.